All right, let's go ahead and get started. Last time I forgot to collect the roster after I did this, so we'll try this again. Just kind of an initial next year name if you're here. If you're not, don't. Today we're going to talk about chemical reactions, balancing chemical reactions, and something very interesting, the mole concept. Now the mole concept can be a little baffling at times, but it's very, very fundamental to chemistry and chemistry calculations. So we're going to do it. Let's start off, however, with simple chemical reactions. We've seen this before. We know that if we take aluminum and bromine, that they react and they form a compound, a new substance, aluminum bromide. We can describe this as reactants being converted to products. This is a chemical equation. The arrow in a chemical equation, this guy, has the same properties as an equal sign. Now what that means is, here we put the things in, aluminum plus bromine, aluminum bromide. There must be the same numbers and types of atoms on both sides, and we will stick in coefficients, these numbers, to make sure that the same numbers and types are in fact present. On this side of the equation, we have two aluminums. On this side, we have two aluminums. Here we have 3 times 2, 6 bromines, and 2 times 3, 6 bromines. You'll also note the little S's and L's and whatever. These indicate the physical state of the substance. So aluminum here is a solid, bromine is a liquid. Our product, aluminum bromide, is a solid. Also use gas, little g for gas, and AQ. AQ means it's in solution in water, aqueous solution. We'll talk about aqueous solutions a little bit later and this. This equation, we'll see in a little bit, can also be expressed in terms of a concept called moles. We would say that this means that 2 aluminums react with 3 bromines, or 2 moles of aluminum react with 3 moles of bromine. And we're going to get 2 moles of aluminum bromide. Again, the same numbers and types. Using the mole concept allows us to describe equations like this very, very simply. In addition to the same numbers and types, mass is also conserved. 2 aluminums, 2 moles of aluminum would be the same as 53.96 grams. This is 479 grams of bromine. If you add them up, it gets 533 grams of product. So mass is conserved as well in the chemical equation. What we're going to look at is the strategy we use to place these coefficients so that we can balance these equations. Now there are lots of algorithms, lots of approaches in how to balance. The balancing we're going to do is going to be fairly simple. Our equations are generally fairly simple. And the approach really is by inspection. We're not going to do some fancy mathematical analysis. We're just going to look at them and figure them out. So let's see how we do this. If we take hydrogen peroxide, hydrogen peroxide, we've all seen it. You pour it on a cut and it fizzes, right? Well, when it fizzes, it's breaking down to give oxygen and water. If we look at this chemical equation that we've written, we notice that it is not balanced, is it? We have 2 hydrogens here, 2 hydrogens there, that's good. But we have 2 oxygens, and on this side we have 1, 2, 3 oxygens. So it's not balanced, or not the same numbers and types on both sides. What we're going to do is to look at this and try to figure out what coefficients we can stick in there to make it balanced. The first thing I always do is I look for odd, even discrepancies. I call it the odd-even rule. We have an even number of oxygens here, and we have an odd number over here. The simplest thing, I think, is to try to see what coefficient you could stick in to make it even on both sides. Okay? All right. Well, oxygen gas is going to come as pairs. Water only has 1 oxygen, though. We could make this side even if we simply stuck a 2 in front of our waters. Now we have an even set of oxygens on both sides. However, by doing this, we now have 4 hydrogens on this side and only 2 on this side. We can fix that simply by sticking a coefficient here in front of our peroxide. Now let's do a bookkeeping here. 4 hydrogens and 4 oxygens. 4 hydrogens and 1, 2, 3, 4 oxygens. This equation is now balanced. Any questions? Kind of magic the way we can do that. Let's go ahead and look at another one. We're taking solid potassium chlorate. We're going to heat it, and when we do, this is going to form oxygen gas and potassium chloride. Potassium chlorate is KClO3. We'll learn this in the next chapter. 1 potassium, 1 chlorine, and 3 oxygens. It's a solid. When we heat it up, it decomposes, and it forms oxygen gas and potassium chloride. Now once again, as we look at this, we see this is not balanced. We have 1 potassium, 1 chlorine, that works fine, but we have 3 oxygens, and here we have 2. Again, using the odd-even approach, I would take this and I would stick a 2 in front of here to make our oxygens even. 3 oxygens, 2 oxygens. We need a coefficient to make this guy even. This now gives us a total of 6 oxygens. Over here, we have 2, but we can make this a 3. And by gosh, now we have 6 oxygens on both sides. The other thing we've done, however, is we've made 2 potassiums and 2 chlorides. So we need to put a 2 in front of this guy. And so it works. There's a trick if you do a lot of these. If you note, we have 3 oxygens here, 2 on this side. Simply 2 times 3 is 6. 2 times 3 is 6. That's what you're shooting for. But again, you don't have to go that deep. You can just simply do it by inspection. Any questions? We'll work some examples in a second. This reaction is actually kind of neat. It's fun. If you ever need to make a little bit of oxygen in the lab to do something, this is what you do. You take this stuff, heat it up, it decomposes, and you oxygen. Demonstrations here. This is the gummy bear experiment. Oh, it's a gummy bear. Yes, it is. Gummy bears are mostly sugar. What we're going to do is take this poor little bear and do mean things to it. We're going to take the gummy bear, which is sugar, in the presence of potassium chlorate. As we heat the chlorate up, it's going to evolve oxygen. Oxygen is going to react with the sugar, that's our gummy bear. We're going to form CO2 and water. Let's watch. Oh! PowerPoint's not going to let me show this. Rats. Hang on just a second. This is worth watching. Okay, I hope this works. There it goes. Here's our potassium chlorate being heated. And there goes our gummy bear. It's not a movie you want to show to young children. But it is really kind of a cute thing to do in lab. And when you're done, all you get is carbon dioxide from the sugar and water. And you form potassium chloride, which is the residue that's left in there. All right, let's go ahead and do some real examples. So take these, and we'll balance these one by one. On your first exam, you will be required to balance an equation, at least one. It won't be real complicated, real difficult. It'll be comparable to, some of these. Our first bit of logic here. We have 2 hydrogens, we have 3 hydrogens, right? We're going to want to make this guy even, so we're going to multiply it by 2s. We want to first put a coefficient 2 in there. That's going to give us 2 nitrogens, and that's what we have here. That's good. And it's going to give us 2 times 3, 6 hydrogens. We have 2 hydrogens here. We would have 6 on this side, so we need a 3 in front of here. And the balanced equation should look something like that. Go ahead and do the next one. When you do these and you actually get one right, it makes you feel so good. Our odd even thing here is going to be our chlorine, isn't it? So we're going to need 2 of these HCl's to match these. That's going to give us 2 hydrogens. Oh, but that's okay. We have 2 hydrogens here, don't we? Still 1 zinc on both sides. All in the world you have to do to balance this guy is that. For our next one here, we have 3 oxygens here, don't we? And only 2 here. We could do our 2 times 3 rule, couldn't we? So we could start off shooting for like 6 oxygens. That way, put a 2 in front of here. Once we have the 2 in front of here, that gives us 4 irons. So we would need 4 here. That gives us 2 times 3 is 6, so we need 3 here. And the chlorines, if we have a 4 here, we have 4 times 3, that's 12, right? So we would need 6 of these guys. This one's a little more complicated, but it looks like that. Let's do 3 more. Yeah.
Are we ever going to see fractionals on tests or no?
Oh, fractional coefficients? No. No. Question was, these are all whole numbers. Yes, they are. We will keep only whole numbers. You can legally put in a fraction, but we're not going to do that. Only whole numbers. 2 hydrogens, that's good. Whoops, not 2. 1, 2, 3 hydrogens. Well, that's a problem, isn't it? We can make this side even if we put a 2 in front of the NaOH. Let's see, if we have a 2 here, we need 2 sodiums. Make it work. And I think, we also need 2 waters because we have 4 hydrogens here. We need 4 hydrogens on this side. Lead reacts with HCl to give lead 2 chloride and hydrogen gas. Not real well, but it does. Again, we have 1 chlorine, we have 2 chlorines, 1 hydrogen, 2 hydrogens, 1 lead, 1 lead. I think all we need to do is double the amount of HCl. That'll give us 2 hydrogens and 2 chlorines. Yep, that worked. And finally, our last one here. We have 1 silver, 1 silver. NO3 is what's known as a polyatomic ion. We're going to deal with those in the next chapter. The concept mapping in this book isn't perfect, okay? So we're dealing with polyatomic ions here, and we're going to learn what they are in the next chapter. Sorry. Just the way they wrote the book. Anyway, we have one nitrate, NO3 on this side, and two of them here. So we're going to have to double this. We double this, we're going to need two silvers. We already have two chlorines. I think that will do it. Two silver nitrates, two silver chlorides. Now the best way to learn to balance equations is just to do them, right? Lots of practice. You will have something on your exam, like I said, comparable difficulty to the ones that we have done here. I have a tutorial that I wrote for balancing. Some of these are very difficult, to be honest. Very complicated equations, but most of them you can manage to figure out, I think. This guy, we'll start off looking here. We have two carbons on this side, don't we? This side we only have one carbon. So we're going to need to put a coefficient 2 in here to do our odd-even stuff. We have 1, 2, 3, 4 hydrogens, and we only have 2 on this side. So we need another coefficient here. If we put a 2 in here, that gives us 2 oxygens. Here's 2 more oxygens, so we need to double the amount of oxygen we have. Start off this way, 2 carbons. That's going to give us 4 hydrogens. Now to make the oxygens work, we need 1, 2, 3, 4, or another 2, 1, 2, 3, 4, 5, 6. So we need a 3 in this spot. Let's do one more. Calcium carbide is an interesting substance. Anybody ever heard of a bank-side cannon? When I was a child, it was a great thing. You take calcium carbide, which is a solid, put it in this cannon with water in it. Calcium carbide reacts with water, and it forms acetylene gas. Acetylene is the gas they use in blow torches. Okay? Once you get a little bit of acetylene gas, then with your cannon, you simply spark it, and it goes off just like a real cannon. It's great fun. Anyway, this is the equation. This is acetylene gas. This is calcium hydroxide. As we look at this, let's see, we have 1, 2, 3, 4 hydrogens. We're going to need at least 2 waters, right? My gosh, that's all it took to get it right. Let's check. 1 calcium, 1 calcium. 2 carbons, 2 carbons. 4 hydrogens, 1, 2, 3, 4 hydrogens. 1, 2 oxygens, 1, 2 oxygens. So that worked. Go ahead and try this. Again, some of these get really, really complicated, really scary. If you get a bad one on the tutorial, just click New Reaction and try again. The same rules apply. You can earn 5 points towards your exam if you can manage to get 10 of these to go for you. Okay? All right, we talked about moles. Well, this is the mole concept. And this is Mr. Mole himself, that's Avogadro. The mole concept. Again, it can seem very complicated, but it's not. Why do we need moles? Remember, in a single penny, we said there were like 28 sextillion atoms. There's no way in the world in chemistry we can do calculations dealing with huge numbers like that. What Avogadro did was develop a way to let us use very large numbers by using the unit mole. A mole, we'll see, is 6.02 times 10 to the 23rd things. Things. It's just like using the word dozen to represent 12 things. This is just a very, very large number. When we refer to this number, we call it Avogadro's number. Now, Avogadro came up with this concept when he was dealing with gases. The observation that he made, and this was, really good for the time, was that if we had 22.4 liters of any pure gas, that the mass of the gas in this thing was equal to the formula mass of the element or compound. Further, he went on to calculate and found that 22.4 liters of any gas, didn't matter what it was, contained 6.02 times 10 to the 23rd particles. Now we're going to talk about the gas laws, and some of this will make a little more sense when we finally do. Formula mass. If you simply take the average atomic mass for each element in a compound and add them up, that's the formula mass. To express that in grams, that number of grams will contain Avogadro's number of particles. We will refer to that as the molar mass, the mass of 1 mole of a substance. Today we actually define it using the isotope C12 here. Anything that contains 6.02 times 10 to the 23rd C12s, the same number of particles, is equal to 1 mole. Remember we talked about isotopes. This is the average atomic mass of carbon. And again, if you were to calculate a formula mass or a molar mass, you would use the average weights from our periodic table. Any questions on the concept here? There's one thing that I want to try to stress to you, and that is the magnitude of Avogadro's number. 6.02 times 10 to the 23rd is an easy thing to say, but it's an absolutely huge. All right. We talked about formula weight. That's just another way of saying molecular weight. We take the atomic weights of all of the atoms in the molecule. Now, these are the average weights, again, from the periodic table. And we're going to add them up. The molecular weight, actually comes in atomic mass units, but we're going to ignore those. Let's look at this amino acid glycine that we had in our hand here. This is the molecular formula. Glycine contains 2 carbons, 5 hydrogens, a nitrogen, and 2 oxygens. If we wanted to calculate the molecular weight, what we would do is look at our periodic table. We remember that carbon is 12.01. We have 2 carbons at 12.01. Look over there. Hydrogen is 1.008. We have 5 of them. We have 1 nitrogen, it's 14.01. And we have 2 oxygens at 16. Multiply all those things out, add them up. This is 75.07. That is the molecular weight of glycine, the compound. That is also the molar mass. So if we had 75.07 grams of glycine, that is equal to 1 mole of glycine. Any questions? Now, the mole concept really, really is interesting and really is useful. This is 1 mole of oxygen in this balloon. So if you weigh this, it would contain 32 grams of oxygen. It would also contain 6.02 times 10 to the 23rd oxygen molecules, O2. This down here is 63 grams of copper. That is 1 mole of copper. Again, this is 6.02 times 10 to the 23rd copper atoms. 100 grams of calcium carbonate. This is chalk. Again, that is 1 mole, 6.02 times 10 to the 23rd things. 18 grams of water. Again, that is 1 mole of water, H2O. Each of these samples contains 6.02 times 10 to the 23rd. Now think about this in terms of chemical reactions. If I told you that 1 mole of copper reacted with 1 mole of water, we would know we would need 63 grams of copper and 18 grams of water. That's how we're going to use the mole concept. This is the actual number, 6.02, blah, 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 blah. Typically, we're only going to use 3 significant figures, 6.02 times 10 to the 23rd. Once again, it's a huge number. It's a strange concept at first, but just think about it as the word dozen. A mole simply represents a very large number. The word dozen simply represents 12, but they just represent a number. Now let's do a silly problem here. If I tell you I have 4-legged dogs and I have 66 dozen of them, how many legs are we talking about? Well, that's simple. Here we are given that we have 66 dozen. We know that there are 12 things in a dozen, so that can be a ratio. And we can find our number of legs. There's our given, 66 dozen. Our ratio. Remember, we have to have dozen in our denominator. 12 for every dozen. We also have 4 legs on every dog. Dozen's going to cancel. Dogs are going to cancel. And we're left only with legs. Do our simple math, and we have 3,168 legs. Okay? Here was our ratio, 12 in 1 dozen. What if we change this problem and we said we had 66 moles of 4-legged dogs? Well, we're going to do this problem exactly the same way. We know that a mole, instead of 12, is simply 6 times 10 to the 23rd. So we'll set the problem up the same way. We have 66 moles as our given. Our ratio is going to be 1 mole is 6.02 times 10 to the 23rd. And then we're going to find the number of legs. 66 moles of dogs. How many dogs in every mole? Well, there are 6.02 times 10 to the 23rd things, it can be anything, in a mole. When you write mole, sometimes you put the E on the end, sometimes you don't. They both work, okay? Again, we have 4 legs in every dog. Dogs are going to cancel, moles are going to cancel, and we're left with legs. It's just a big number, isn't it? So we're going to multiply 66 times 6 times 4, and we get 1.58 times 10 to the 26 as our legs. Now our significant figures here are off, aren't they? 4 legs per dog, that's a simple ratio. We're dealing with 4 significant figures, 3 significant figures. We should round this to 1.60, or 1.59, sorry. All right, so that's the concept. We're simply going to use mole as a number, just like it was a dozen. So let's do a real problem. If a mole of hydrogen gas contains 6.02 times 10 to the 23rd hydrogen molecules, how many in half a mole? Remember the tutorial that you did, that I hope you did, on exponents? Here we are given half a mole as our given. We know that there are 6.02 times 10 to the 23rd in 1 mole. So we can set that up as our ratio. Again, here's our given. Our ratio. We need to set this up so that mole is in our denominator, right? That's how we do it. 6.02 times 10 to the 23rd molecules in a mole. Mole and mole are going to cancel, and we're left only with molecules. All we're going to do is multiply 0.5 times 6 times 10 to the 23rd, and we get 3 times 10 to the 23rd. Let's do another one. We have 3.27 times 10 to the minus 9 moles of a gas. How many gas particles does this represent? Well, we know how many particles there are in a mole, right? We all remember the song. 6 times 10 to the 23rd. So, what we're going to do is take this as our given. Our ratio is simply particles per mole, and we're going to multiply them out. Our setup. Here's our given. That's the number of moles we have. Our ratio. Excuse me. Our ratio, maybe not. Our ratio, particles per mole. Once again, the ratio is set up so that mole and mole cancel. We simply have to do our exponent, multiply those guys, and we're going to add the exponents, minus 9 and 23, and we get about 2 times 10 to the 15. This is the same exercise again that you did in the tutorial. Practice it, make sure you have it, make sure you can do it on your calculator, okay? Because everybody's calculator does exponents slightly differently. Yeah?
I had 10/14.
Hmm?
It was 10 to the 14th power.
To 14?
Yes.
Oh, okay, well, maybe I did it wrong.
Okay, I
You know, again, I sometimes put mistakes on the slides on purpose, just to see if you're paying attention. All right, here we have 17.8 grams of magnesium hydroxide. The molar mass of that is 58.32 grams in every mole. How many moles is that? Well, think about it. We know that 58 grams is 1 mole, right? And how much do we have? We have 17.8. So it's going to be some fraction of that mole. We are given our mass here. We know the molar mass. So we can do our simple algorithm. Take our mass. We're going to use this as a ratio, but we have to have grams in our denominator. So there's our given. Our ratio, we're going to have to flip this upside down, so grams is in the bottom. You can say 1 mole is the same as 58 grams. Makes it, makes sense to you. Now we're just going to divide these two together. And I hope I got it right. And it's about 0.305 moles. This is an actual old exam question. If a mole, this is another exam question, if a mole is 6.02 times 10 to the 23rd, what's 10% of a mole? Well, 10% is 1/10, isn't it? We can use our given here as our number of molecules. For our ratio, what is 10%? Well, it's actually 10 over 100, isn't it? So here's our ratio. Basically, we're going to move our decimal over, and it's 6.02 times 10 to the 22nd. You could probably just do that one in your head. Any questions? Now, how do you get good at this? Just like you do at everything else in chemistry. Oh, didn't do the answer. Actually, none of these are the same as this, are they? This is 6 times 10 to the 20. We're looking for 6 times 10 to the 22. 0.6 times 10 to the 22. That would actually be 6 times 10 to the 21. So none of those are correct. Everybody hates it when none are correct. All right, everyone loves tutorials, however. This is mole mass tutorial. There are 2 of these, slightly different. This one is just a table, just like density 1 and density 2. We are given that we have 1.03 moles and our mass is 104 grams. We're looking for the molar mass. All right, our logic here. If 1.03 moles weighs 104, what does 1 mole weigh? if we take our molar mass, our definition of molar mass is the mass divided by the number of moles, right? That's our definition. We are given mass, we are given number of moles. All we have to do is substitute in here, and we get 100 grams per mole. Simply remember the definition for all these. This is all you need to know. Molar mass is mass divided by moles. Try another one. Here we're given the molar mass, we're given the number of moles. What's the mass of our substance? Remember, molar mass is mass divided by moles. Simply want to solve for mass. Mass is going to be moles times molar mass. You do the solution. So all we have to do is take our number of moles, take our molar mass, multiply them together, and it should be 163. This is the word problem version. But they're very simple though, not like density was. How many moles is 87 grams of copper? Now we are given that 1 mole of copper is 63.5 grams. So here is our given. Here is our ratio. Remember moles. It's going to be mass divided by molar mass, right? All we do is substitute. Here's our mass. Here's our molar mass. And that's equal to 1.38 moles. All of these can be solved just by remembering that molar mass is mass divided by moles. All you have to remember. And remember, on the exam, you get to bring your 3x5 card, right? So, if you have trouble with this, write it down. Molar mass, mass divided by moles. Let's do one more. Here we have 0.243 moles of lead. We know the molar mass of lead is 82. What's our mass in grams? Remember, molar mass, mass divided by moles. Therefore, molar mass times moles gives us mass. Molar mass times moles gives us mass. Simply substitute. Moles 0.243, molar mass 82. We're looking at 19.9 grams. Now this one is just a cute variation on this. Every now and then you'll get one of these come up. We have a sample of an element. The mass is 29.14. I tell you that this is equivalent to 2.7 moles of the element. What is it? How are you going to do this? We are given mass and moles, right? If we take mass and divide it by moles, we get molar mass, right? All we have to do is look at our periodic table and match up our molar mass. Going to divide mass by moles. That gives us our molar mass. Turns out to be 10.8 grams per mole. Now we look at our periodic table, and you will get a periodic table like this on your exam. And we find something that weighs 10.8. That's all. Well, let's see. Oh, how about boron? And once you've figured out that it's boron, you simply go back. Whoops. You would go back and type B in here. And of course, you'd get it correct. So you'll get this is the second tutorial. I forgot what it's called, but I'll review them in a little bit. But all you do is find the molar mass on the periodic table, and you should be good. All right. In addition to dealing simply with numbers of moles, we can also look at a formula for a compound, and we can express this in terms of a ratio also. Mole ratio, it's called. It's simply the number of moles of each in a compound. If we had 1 mole of HCl, think about it. If we had 1 molecule of HCl, we would have 1 atom of hydrogen, right? Therefore, 1 mole of HCl and 1 mole of hydrogen. Simple ratio. Because we know how much these weigh, we can use this approach to calculate a mass percent. Now in our lab next week, we're going to do mass percentages. You're going to calculate one. So this is going to lead into that. We know that 1 mole of hydrogen is the same as 1.008 grams of hydrogen. We know that from the periodic table. Our molecular weight of HCl is going to be 1 plus 35.5 grams of HCl. If we simply divide these, we would get 0.02, convert it to a percentage by multiplying by 100, and we could say there that HCl is 2.84% hydrogen. Now again, all you do, look at your compound. If we're interested in hydrogen, it's just the mass of hydrogen, the mass of the compound. Multiply it by 100, and that gives you percentage. Let's try one. Here we have calcium fluoride, 1 calcium, 2 fluorines. Calculate the percentage of fluorine. Well, step 1, we look at our periodic table over there. We see that the mass of fluorine is 19 grams per mole. Okay? To get our molecular weight for calcium fluoride, we need to look over here, find calcium. 1 calcium plus 2 fluorines gives us a total of 78. Simple addition. In calcium fluoride, there are 2 fluorines for every calcium fluoride, right? Every fluorine weighs 19, so that's 2 at 19. Every mole of calcium fluoride is 78. We do our very simple calculation here, 2 times 19 divided by 78, and we get 0.48 or 48%. So you find your compound, you add up the molar mass, that's the molecular weight. If you have more than one, remember you have to multiply it. Once you get your fraction, this guy, simply convert it to a percent by multiplying by 100 and of course making it red. Let's do another one. Scandium chlorate. Now, we don't know what that is yet. We will next week. We're trying to figure out how many the percentage of oxygen. Now, according to the periodic table, every oxygen is about 16 grams per mole. We would go to our periodic table, find out that scandium-3 chlorate has a molar mass of 295. Did that just by adding it up. On an exam or something, I would probably give you all these numbers, so you don't even have to add. Molar mass of oxygen is 16. Molar mass of scandium-3 chlorate is 295. Set up your mole ratio. That's number one. How many moles of oxygen in every mole of this? Well, that requires you to read the formula. Every chlorate here has 3, so that's 3 times 3, 9 oxygens. Nine oxygens in every scandium chlorate. Again, 3 times 3. Every oxygen weighs 16. This stuff weighs 295. Excuse me. Okay, I don't know how that happened. Okay, I think back online here. Every oxygen weighs 16. 9 of them. This stuff weighs 295. And we're dealing with 48, 49%. Simple percentage. Let's look at one more. If we have 454 grams of magnesium fluoride, how much fluorine do we have? Now, how are you going to solve this guy? Basically, we have to know how many moles this represents. We know that every mole of magnesium fluoride is going to have 2 fluorines. So our logic, again from our periodic table, every fluorine is 19 grams. We add up magnesium fluoride at 62 grams. Our given, which is our 454, going to be multiplied by the ratio, the molar mass as a ratio. Putting it all together, We have 2 moles of fluorine in every mole of magnesium fluoride, right? That's 38 grams of every 62. So here's our given. Here's our ratio. Magnesium fluoride cancels, and we're left with fluorine. We have, in our sample, 276 grams of fluorine. All right. This problem is probably a little bit too complicated for an exam, but the basic percentage calculations are not. And so I did a simple tutorial based on calculating percentages. This tutorial will give you a compound, its molar mass, and we're going to calculate the percent for each of the elements. So, in our nickel hypochlorite, nickel 2 hypochlorite, we would have 1 nickel, 2 chlorines, 2 oxygens, right? 1 mole of nickel weighs 58. This stuff is 161. Therefore, to do the nickel, we simply say we have 1 at 58 divided by 161, or 36%. When you do the tutorial, don't type in percent, just a number. For chlorine, we have 2 chlorines, each one weighs 35.4. So that's going to be 2 times 35.4 divided by 161. 43%, 44. And finally, oxygen. We have 2 oxygens at 16. It's 2 times 16 divided by 161, roughly 20%. Now, if you do this tutorial, and again, you can earn points if you do, you'll note that these don't always add up to 100. Sorry. They're always close, but they're never exactly 100. That's just a programming error, but they're close enough. Go ahead and try to do this one yourself. Calcium chlorite, 1 calcium, 2 chlorines, 4 oxygens. Go ahead, set it up, and calculate it for all. For calcium, we have 1 calcium, don't we? That's 40 grams. Divided by our 175 gives us our percentage. 22.9. We have 2 chlorines. Each one is 35, so that's 70. Divided by 175, or 40%. And finally, our last one. We have 1, 2, 3, 4 oxygens at 16. So 16 times 4 divided by this, we're at 36.6. Once you work this twice, again, you will earn your 5 points towards the exam. All right. The last real concept that we have to address in this chapter is the concept of molarity. As you know, lots of chemical reactions can happen in solution. Okay? They just happen in solution. If we know the number of moles of something that are in the solution, then we can predict how many moles of this are going to react with so many moles of this from our balanced equation. Molarity is simply defined as the number of moles divided by the liters of solution. This is 1 liter of solution, and this is 1 mole per liter. That's all in the world you have to remember. For molarity, the number of moles in 1 liter of solution. All right, this is a volumetric flask. We'll actually use these in the lab. They're expensive. They have a little tiny etch line here. When the flask, the neck here is filled up exactly to that line, that is a certain volume of solution. Here we're dealing with a 1 liter flask. When we talk about molarity, the abbreviation we'll use is the uppercase M. Uppercase M. Don't do a lowercase m. When you get to general chemistry, you will find that lowercase m represents molality, which is totally different. So uppercase M. To make a solution of known molarity, you would start off with an empty flask. Here's a little etch line, that's 1 liter. What's our simple definition here? Number of moles divided by number of liters. That's all in the world it is. So you would take a certain number of moles and you would put it in your flask. Here it is. Once you get your stuff in there, solid or liquid, then you're going to add water to bring it up to the 1 liter mark. Now you know you had so many moles, that's the stuff you put in, and it's in exactly 1 liter. If we had put 1 mole of stuff in, this would be a 1 molar solution, 1 mole per liter. All right, again, it's a very simple concept, very simple ratio. Let's do it in a problem. Here we have 3.25 grams of sodium bromide. We have 1,250 mils of solution. What's the molarity? Well, 1 mole of sodium bromide is 102 grams, isn't it? We only put in 3.25. This is 1,250 milliliters. Remember, there are 1,000 milliliters in every liter. So this is 1.25 liters. All right. We need to know how many moles of sodium bromide this is. We can do that, can't we? Because we know how many moles or what mass is 1 mole. So simply this divided by that gives us moles. Next, we need to divide this by the number of liters. Again, that's going to be 1.25. This is going to give us our number of moles, isn't it? This is how much sodium bromide we had. This is how much 1 mole weighs. Grams are going to cancel. moles are going to come up top. And finally, our volume here is 1.25 liters. So this is moles divided by liters. The grams cancel. Mole comes up top because it's a negative exponent in the denominator. It comes up top. And we're left with 0.02 moles per liter. We would say the solution is 0.0253 mole, uppercase M. All the work we did, calculate the number of moles divided by the number of liters. This is sodium acetate. We have 6.47 grams of it. 1 mole weighs 82. We have 1450 mils of solution. We have to convert that to liters. Use the same logic. Calculate the number of moles and divide it by the number of liters. Go ahead and do that. Our number of moles is just going to be mass divided by molar mass. That's actually a neat thing to say. If you want something to remember, to say before you go to sleep at night, mass divided by molar mass is moles. You can write it on your card, or you can just recite it every night when you go to bed. Mass divided by molar mass is moles. If this is the number of moles, we simply have to convert this to liters. And that's 1.45 liters. Our grams are going to cancel. Per mole are going to come up top. Do our simple calculation. 0.05 moles per liter, or 0.0544 molar. Any questions? Let's skip ahead here to the molarity tutorial. There are 2 of them. Again, this is the table version. We are given the number of moles. We are given the number of liters. Here we simply have to calculate molarity. Remember, molarity is going to be moles divided by liters. Molarity, number of moles divided by number of liters. We are given 0.976 moles, 2.15 liters. This is 0.454 moles per liter. Again, when you type in these things, don't use units, just the numbers. Here we are given molarity. We're given the moles. What's our volume? We remember molarity is simply moles divided by volume, right? So moles divided by molarity will give us volume. Moles divided by molarity gives us volume. Do our simple calculator substitution, do our calculation, and we have 4.26 liters. One more variation here. I'll hush and let you do it. We are given molarity, we are given volume. Moles divided by volume is molarity. If moles divided by volume is molarity, then molarity times volume gives you moles. Molarity times volume gives you moles. Simply substitute, do your calculation, and we're looking at 0.365 moles. Now there's another molarity tutorial that's a little more complicated. You don't have to do that one. But do this one. Again, it's not difficult, and you'll get your 5 points. All right, let's do one more concept here. We talked about molecular formula. There's another type of formula that we will use called an empirical formula. It's simply the lowest whole number ratio of elements in a compound. That's all it is. This is glucose, sugar. This is C12, C6, H12O6, right? The lowest whole number ratio here. Well, we have 6 carbons, 6 oxygens, 12 hydrogens. The empirical formula would be CH2O. The lowest whole number ratio. Now look at that, CH2s, H2O. Ever heard of a carbohydrate? That's where the term comes from. Carbon, carbo, H2O is water. Carbohydrate, that's where it comes from. This is acetic acid, vinegar. It is CH3, COOH. We have 4 hydrogens, 2 oxygens, 2 carbons. Its empirical formula is also CH2O. Simplest whole number ratio. Acetic acid is officially a carbohydrate as well. In fact, when you metabolize glucose, you can form acetic acid in your body. All right, this is glucose, and I just explained it's a carbohydrate. This is one of the neatest experiments to do, except you really can't do it unless you have good hood. What we're going to do is take glucose, and we're going to add sulfuric acid, concentrated sulfuric acid. What sulfuric acid will do is remove the water from glucose. When it does this, all that's left is the carbon. So very, very carefully, we will add sulfuric acid to our sugar. Stir it up a little bit, very carefully. Now you'll notice it starts to get ugly. That means the reaction has started. Getting uglier and uglier. And all of a sudden, it starts getting really hot. As it does, water boils off as steam, and this is the carbon from the carbohydrate. And it emerges as this ugly-looking black column. Really kind of a cute experiment. C6H12O6 in the presence of sulfuric acid gives water and carbon. Isn't that cute? All right, this is a molecular model, isn't it? Let's just make sure we understand about, let's do empirical formulas first, sorry. Go ahead and look at these compounds and just write the empirical formula for me. Acetylene we saw is what they use in welding torches and whatever. It consists of 2 carbons and 2 hydrogens. What is the lowest whole number ratio? CH. This is what acetylene looks like. Has a triple bond right in here. Benzene. Benzene's a very nice solvent. When I was an undergraduate, I worked in a lab where we made polymers. Now, when you make polymers, they're big, long molecules. They're sticky and gooey and nasty and whatever. And you get it all over your hands. Okay? The only thing that would take this stuff off effectively was benzene. So by the sink, we had this little jug of benzene. We'd all wash our hands. Can't do that anymore. Benzene is now considered carcinogenic. And you can't even touch the stuff. But it's a darn good hand wash. We have 6 carbons and 6 hydrogens in benzene. What's the ratio? Every carbon has 1 hydrogen. This is what benzene looks like. What's the empirical formula for water? Well, this is the lowest whole number ratio, isn't it? 2 hydrogens, 1 oxygen. Hydrogen peroxide, we saw fizzed. 2 hydrogens, 2 oxygens. The empirical formula is simply HO. Very simple concept. Why do we care about empirical formulas? Because one of the things you do in chemistry is analyze things. When you analyze something, the number that you get, the thing that you solve for, is the empirical formula. So that's why empirical formulas are important. All right, finally, let's do molecular models. Just make sure that everybody knows what we're talking about when we do these things. The 2 types that we'll see in this class are referred to as ball and stick because they look like little balls and little sticks. And we'll see space filling every now and then. These are actually on the same scale. To do a space filling model, what you do is you calculate how large the electron cloud is for every atom, and you simply show this as a sphere. Typically, you draw the limit at about 90% of the electron cloud. So this gives you an idea of how big the molecule really is. This is nice because you can see all the bonds nice and clearly. When we do molecular models, there's a convention. Carbon is typically black, gray, something like that. Hydrogen is almost always white. Oxygen is almost always red. And nitrogen will be blue. If you look at chlorine gas has kind of a light yellow color. The model for chlorine is light yellow. Bromine we've seen before. Well, bromine is brown, little brown balls. Iodine would be purple. Typically, you try to match the color of the element. These are almost always standards. We saw our friend glycine. This is a ball and stick glycine. If we wanted to convert this to the molecular formula, what we would do is look at the number of carbons, hydrogens, and oxygens. We see that this has 2 carbons. It has 1, 2, 3, 4, 5 hydrogens. It has 1 nitrogen and 2 oxygens. We could convert this to our molecular formula simply by writing it in our standard way: 2 carbons, 5 hydrogens, 1 nitrogen, and 2 oxygens. Now, how do you know which ones to put first? Well, you just have to know. Typically, compounds that contain carbon are considered organic compounds. Organic chemists are very arrogant. Carbon always has to be first. Hydrogen has to be second, and then you stick the other stuff on. So carbon first, then hydrogen, and then the other stuff. Remember, we've also talked about diatomic elements. Hydrogen exists as H2, nitrogen is N2, oxygen is O2, fluorine is F2. Here's chlorine at CO2. Here's a model for bromine. Bromine is brown. Br, Br2. Iodine would be purple. You need to kind of know these guys, because when we do reactions and stuff like that, if I tell you something reacts with oxygen,